Hello everyone, good morning, good afternoon, good evening, wherever you are. My name is Petr Kastovsky and I'm with BXD, the Barefoot team at Intel, where my role is product management for Tofino X. And I'm going to explain what Tofino X is in the next slides. But before we do that, let's note some legal notices and disclaimers. I will pause on this slide for a brief moment to make you aware of these notices. And so let's look into what Tofino X is by first talking about the Tofino switch ASIC and the associated tools. As you may know, Tofino is a programmable Ethernet switch. The language used for programming Tofino is called P4. It is an open source language managed by Open Networking Foundation, which is backed by a very strong community, including leading cloud service providers like Microsoft, Google, or Alibaba, and also communication service providers or telcos like AT&T, China Mobile, DT, and also vendors including Samsung, Cisco, and of course Intel. So in order to define the switch functionality, we need to start with the P4 code. The P4 code is processed by the compiler, which generates necessary inputs for the Tofino ASIC itself. And it also creates some information for the API layer that needs that information to be able to talk to the ASIC and the code loaded in the ASIC. So this really makes the whole platform fully programmable and provides a programmable packet processing pipeline, which is primarily built for the traditional command switching applications like leaf spine and top-of-rack switches. But thanks to all that flexibility, it can be also used in other applications, including the packet brokers, load balancers, traffic testers, and different types of gateways. Well, some of these applications require, for example, very high number of entries to be stored, or it sometimes require also some traffic management capabilities with very deep buffers. And even though Tofino is very flexible and very capable, probably the most flexible switching ASIC out there, some of these features go beyond what can be put onto the chip within the limited real estate. And that's a moment where the FPGA comes into play, and that's when we enhance the Tofino capabilities by adding Intel FPGAs. By doing so, we're able to increase the table capacities by two orders of magnitude, and not only the table capacities, but also the buffer capacities. So these are the two major groups of use cases: the extra large tables, where by adding the FPGA into the system, we can achieve, up to hundreds of millions of table entries for the extra large tables. And for the extra large buffers, by adding an FPGA, we are able to get up to tens of gigabytes of high-speed deep buffers. Now, there are different types of applications that can benefit from this capability in both cloud networks and also the telco communication service providers networks. To give some examples of the cloud applications, those are different types of gateways, like that implement different types of functions like firewalling, load balancing, different types of tunnel terminations, and translations. But for example, the load balancing functionality can be also standalone in the data center. In the service provider networks, again, different types of tunneling and translating functions, routing functions, network packet brokers, or even 5G user plane functions. The extra large buffers are typically useful in the service provider networks that are oversubscribed and require traffic management and traffic shaping functionalities. And these are typically needed in use cases like broadband network gateway, user plane function, access gateway function, and others. But the list doesn't end here, as the FPGA is a fully programmable, very flexible device. We can implement other functions. We can implement different building blocks that can be used to accelerate applications like machine learning or AI, cryptography, regular expression matching for DPI acceleration, and so on. Now, there are different ways how to, build these systems. We are sort of looking at two different applications. So starting from the left, we've got Tofino providing all the front panel connectivity, having FPGA as a look-aside function that can be selectively invoked when the program in the Tofino decides so. And all is complemented by Xeon CPU that can provide high-level application functions. On the right side, the difference is that both Tofino and the FPGA are providing part of the front panel connectivity, and this architecture can have different benefits and implications that are use case and application specific. So we talked about the architectures. Now there are different form factors that we can see or we can leverage to build these architectures. So starting with the sort of disaggregated approach with a switch system and FPGA SmartNICs that can be connected through front panel ports. Then go into switch server integrated platforms where all the components are actually available in one rack mountable device. And the last is the chassis platform where we can have different sleds, blades, or modules with the different resources, compute, storage, networking, and these can be scaled depending on the application requirements. Now, this is very flexible and very performant combination. And in order to take benefit of that combination and of the capabilities, and also to demonstrate what can be what can be built by using these chips, we've developed a layer 4 server load balancing accelerator. As you may know, load balancing is a key service in the data center that guarantees efficient utilization of the data center resources that are typically compute and storage. As the data traffic is continuously growing, as you can see on the slide, today's data centers need to handle tens or even hundreds of terabits of traffic. And as the traffic goes up and up and up, the switch server-based load balancing solution that can handle multiple terabits of traffic is an effective way of handling such a high traffic rate while keeping the total cost of ownership of such a system under control. So how does that look like in the network? Well, we can see the typical configuration where a client traffic coming to data center needs to go to the SLB software first, which is the blue box at the bottom. In this case, it is implemented by IPVS, which is part of Linux kernel. It's an open source layer 4 load balancing software. And this software makes a decision which backend server will deliver the content to the client and forwards the packet to the client accordingly. Now, in order to scale the number of servers, number of backend servers that are actually generating the revenue, we introduced the server load balancing accelerator, which is the pink box described as SLBA. And the flow is very, very similar to the previous case, at least at the beginning of a new session. The client traffic goes into the data center. It first needs to go to the IPVS for the software to make a decision where to forward the traffic. And when the software makes that decision, it not only forwards the client traffic to the right backend server, but it also sends that information about this pairing to the SLBA connection cache. And this SLBA cache is then able to process all the packets of the same flow without involving the IPVS, the blue boxes at the bottom. And as this is done in the data plane, leveraging the switch ASIC and the FPGA, it reduces the latency of the overall processing. So from the client point of view, it's actually an improved experience because the content is delivered faster. Now, there are different ways how this can be deployed in the data center. And the most likely scenario that we see is by having the SLBA connected to the leaf spine fabric. The other benefit of disaggregating the data plane and the control plane is that these can be scaled independently. So now the data center operator is able to deploy as many SLBAs as they see fit, and they can independently also scale the software components. And also by having this connectivity to the leaf spine fabric, independent of all the other components, this can be added into the data center without performing any forklift upgrades.
Hey, Peter, I got a question for you. This is Jeremy. As you're going through this, to help, myself and maybe some other viewers, can you kind of set the context of the market, the kind of the customers that would be buying this product and using it, because my background actually includes a bit of network processor programming from a long time ago. But I was at a vendor, we would buy chips like this and we would build these types of products. But it doesn't sound to me that this would be necessarily a product that an end customer would buy, or maybe end customers are buying this and I'm out of touch. So I'm kind of curious if you can kind of talk about the market segment that would be buying these types of products.
Sure. Thanks for the question, Jeremy. There are different paths to the market, and as you can imagine, the hyperscalers are customers on their own and with their own capabilities of taking such a technology and customizing it, deploying it on their own. For the other customers that do not have that scale and that high number of resources internally, we are working with the ecosystem to sort of deliver more packaged solution. So, and on the other hand, as this is really a terabit level device, this is suited and focused on high networks. So typically the data center type of applications, or maybe high-end service provider networks.
Okay, and does Intel provide like software applications or kind of getting started software packages that customers could kind of take and then kind of customize and make it their own, or do they have to write code kind of from hello world and start from scratch? Can you talk about the kind of the software ecosystem that's around this?
I'm gonna talk about the functionality in more detail on the next few slides, but when it comes to the ecosystem, we have actually developed the whole software stack that runs on the SLBA device at Intel, and yeah, we are going after different monetization strategies. So let me move to the next slide. And on this one, I would like to give you a little bit a closer look at what such a system does. The diagram that you can see on the slide is a simplified diagram of the let's say switch server, or I should say all the components or the blocks which are in the gray box are sitting inside of the switch server. Now you can see there's a switch CPU, there's Tofino, there's FPGA or multiple FPGAs, and this diagram is relatively high level. It doesn't describe all the functions, but it helps us to understand what the system does and how it operates. So let's say a new session comes into the data center, new client requests the content. When that happens,
can I ask a quick question?
Sure, go ahead.
Can it also detect the embedded IP address in a VXLAN, for example, as a few data centers use that as overlay?
Definitely. The strength of P4 and Tofino is in the ability to handle arbitrary, tunnel stacks and encapsulation protocols. So even if it doesn't offer that capability from the get-go, there's always a possibility to provide it as a field upgrade. So all the different encapsulations, tunnels, that's very easy and straightforward. So when a new session comes and the system knows or recognizes that the TCP flags, by inspecting the TCP flags that this is a new session, it sends that session to one of the SLBs to the software. Now, what the SLB does, it handles the packet appropriately and also sends the information back to the system to set up the entry in the caches. So when a packet of the same flow comes in, it's going to be in the Tofino hot cache. Now, if that session and the Tofino, based on the provided information, would forward the packet to the right backend server straight away. Now, if that session becomes, let's say, less active, it will get eventually replaced in the hot cache, in the Tofino, which can be, let's say, on the order of hundreds of thousands in size. And when it gets replaced, the Tofino, the lookup in that hot cache generates a miss, and the Tofino generates a lookup request to one of the FPGAs. Now, one of the FPGAs that's asked to perform the lookup performs the lookup and returns the result. If there was a hit, the result the lookup result is used to send the packet to the right backend server. Now, if that session was quite inactive and got replaced in the warm cache as well, and the warm cache is typically in the size of tens of millions of entries, the system would generate the miss also in the warm cache, and the packet would be sent to one of the SLBs for the eventual processing. So this is in high level a description of the key functions that we have implemented in the Tofino and the FPGA. And now, depending on the actual hardware configurations, such a system can provide tens or even hundreds of millions of entries while achieving hundreds of millions or even billions of lookups per second. The switch server is based on a programmable hardware that can be modified or updated to support different types of protocol stacks. To sort of follow up on Peter Jean's, sorry if I butchered your name, question. And yeah, all the different types of redirections, tunnelings, and encapsulations are supported or can be supported or upgraded in the field. As we are storing very high number of entries, as I mentioned, it can be up to tens or even hundreds of millions. We also need an efficient way to update these entries, and for that we use a data plane table management. And I will talk about our capability to detect DDoS attacks, our defense mechanism, as well as the operating system and interface to the outside world on the next two slides. So now, when it comes to the DDoS detection and defense, we're able to detect SYN flood attacks. We do that by continuously monitoring the SYN packet arrival rate, which is done in the Tofino data plane. The data plane regularly exports information about the SYN arrival rates within a certain time window, and the local CPU is then able to detect some spikes or anomalies in this traffic. And based on such a detection, a trigger defense mechanism, which is SYN cookie based. Now the legitimate clients would respond with the correct acknowledgement, respecting the cookie, and based on that they would be whitelisted and let into the data center. The rest would be ignored. The algorithm is stateless and it consumes very little resources, and it runs at the speed of the switch data plane, which is up to 6.4 terabits for the first generation of Tofino and up to 12.8 terabits for Tofino 2. The software stack is based on Sonic, which brings all the latest innovations in the cloud-native containerized microservices to the table. The interface to the outside world is based on Redis, which gives us high-performance in-memory database that we need to be able to handle high number of new flows and sessions coming to the data center.
Quick question here. So is Sonic and Redis running on the actual Tofino chip itself, or is that part running separately and then the Tofino's talking out to it?
So the Sonic, if I go back a few slides, is actually on this slide on the upper right corner. So it's a software stack that runs on the switch CPU. It includes all the drivers and talks to the Tofino and controls, part of the functionality like routing. All right. So now I'll show you some of this in a short video demo in action. And before I do that, let me quickly describe the testbed that we used to record this video demo. We've got let's say minimalistic testbed, as we don't have that many data centers around to play with. So we've got one client connected to the SLBA connection cache, and as this is equipped with Tofino, it also serves as a switch. So we are actually, in this case, combining the functionality of the load balancer and the switch in one box, but it's just for the simplicity. We are using iPerf to generate 100 sessions from the client, and we are doing that by 10 sessions at a time. And in parallel, we're monitoring round-trip latency by NetPerf. So let me try to show you how it works. As I was describing throughout the presentation, we're leveraging the combination of Tofino FPGA and memories connected to the FPGA to provide very large table capacities. I've just briefly paused the video. In this configuration at this point in the demo, the traffic is going through the SLB, through the IPVS. So as you can see, the latency is somewhere around 76 microsecond in the best case. Now, as we will activate the SLBA functionality, the latency drops down to 52 microsecond. And now we will start loading the system. Let me pause the video again and describe what we are seeing on these charts. So starting from the left, we've got the left upper corner, we've got the CPU utilization on the SLB server. We've got SLB throughput, and then we've got a number of SLB active connections. So these are the statistics coming from the box that runs the software load balancing implementation. On the right side of the screen, we can see at the top the backend server CPU utilization. Then we can see backend server throughput, and then some additional statistics like the latency, which is measured end-to-end, and number of entries loaded in the Tofino and the FPGA. Now, what we can see as we are loading the system with the 100 sessions, the SLB throughput spikes here and then as it receives the new sessions, but the CPU remains basically idle. That's because just the initial few packets of the session are processed by the SLB, and then the entry is pushed into the Tofino and FPGA, and then the SLB is available to serve new client requests. And the second sort of run is just a simple demonstration that we can really scale the capacity of the system by preloading a high number of entries. You can notice the SLB cache entries number in the FPGA, which is above 1 million entries, and we're getting the same performance numbers even with this high number of sessions in the system. So this is really a demonstration of the scalability in terms of the throughput as well as in the capacity. That was it for me. I would encourage anybody interested to see this live to let us know. We're very happy to present this, and I'm happy to answer any questions.
Just kind of thinking about use cases here. Do you see any use cases for this in like microservices architecture, container-based architectures?
Sure. I mean, from the load balancer point of view, or from the load balancing point of view, the need to support more sessions will only grow with the microservices, because there will be more endpoints or instances of compute in the network, and therefore the capacity of the sessions will need to grow. So I believe this architecture actually favors this direction.